So the next unsupervised learning task is dimensionality reduction. What does this mean? Imagine a car or a plane or a robot or a human with thousands of sensors recording lots and lots of data, perhaps at hundreds or thousands of hertz, right? So um, data is streaming through to say the central nervous system uh, in the case of a human, or um, some central processing unit in the case of, say, a computer, and perhaps megabits or gigabits or maybe terabits per second. Even a single image is many thousands of numbers, as we have seen. Um, it may be the case that not all of this data contains new information, right? So, and it's quite possible that data from different sensors are correlated. And even from, if a sensor is more like a video camera, it may be that neighboring pixels don't have too much independent information. The information is sort of related. So that may be the case. Okay, so but overall, the question is then, if perhaps all these sort of data sources do not have independent information, can we somehow take all this information and reduce the dimensionality of the data? In other words, instead of trying to pay attention to thousands or millions of numbers per second, let's say, can we get away with just paying attention to or compressing the data into, let's say, 10 numbers or 100 numbers, right? So this is what we call dimensionality reduction. Here's a simple example. Imagine, for instance, data from two sensors, X1 and X2. And if you plot X1 versus X2 for some system, maybe X1 versus X2 looks like this. Okay, so, or X2 versus X2 may look like this. Okay, what is the difference between these two streams of data? Here, what it looks like is that if you knew X1, then there's a pretty good chance you can predict X2 very well, because it looks like X1 is linearly related to X2 or vice versa. Here, on the other hand, the data points seem largely uncorrelated in the sense that X1 is not necessarily correlated with X2 or vice versa, right? So if you're in this case, even though there are two numbers, X1 and X2, to pay attention to, it may be that if you knew X1 pretty accurately, you can know X2 pretty well as well, just informally speaking. Whereas in this case, knowing X1 doesn't give you too much information about X2, too much additional information about X2, okay? So that's the difference between these two situations. So in this case, we could say something like, even though this is two-dimensional data, perhaps we can approximate the data set as being one-dimensional because it seems to lie on a line. Not exactly, but approximately. Here, on the other hand, it's two-dimensional data, and you can't really sort of reduce it to one dimension pretty well. Okay, so that's what we are saying here. If your data looks like one, knowing X1 gives a pretty good idea of X2. They're not very independent, informally speaking. So we say the data in one is closer to one-dimensional, but the data in two is more two-dimensional, right? There is no systematic relationship between X1 and X2 here. Here's another set of data points. Is this one-dimensional or two-dimensional? We would call this sort of more one-dimensional as well because, again, rather than the data points lying on a straight line, roughly, they're lying on a curve. A curve is a one-dimensional object, right? Given x1, we can tell what x2 is, at least up to a few different options. So 3 is like 1, except the curve that it lies on is non-linear. So this is what we are referring to when we say dimensionality reduction. if the situation is more like this, perhaps we can get away with just keeping track of one number or a few numbers rather than all the numbers. Okay, so that's what we mean by dimensionality reduction. Given m-dimensional data, we try to see if we can represent the data reasonably accurately with fewer variables. In other words, is the m-dimensional data well approximated as lying on a lower dimensional surface? Which by lower dimensional, we mean less than m dimensions. A classical method for doing this is called principal component analysis. And then a more recent neural network-based method for doing this is called autoencoders. Okay, so we'll first look at principal component analysis. This is a very classical method that's at least, I don't know, 70, 80 years old, maybe 200 years old. It is used in mechanical and aerospace engineering, in fluid mechanics. It has sometimes been called proper orthogonal decomposition or Carhunen lobe projection. It's also essentially the same as singular value decomposition or eigendecomposition of appropriate matrices, as we will see in a minute. Okay, so principal component analysis, PCA. We shorten it to PCA. In fluid mechanics, they may call it POD, proper orthogonal decomposition. More or less the same thing. Okay, so here's the idea. What's PCA? Say we have data that looks like this. We have a couple of variables that we're keeping track of, and each of these is a different data point. So we're just getting these data points and we're plotting them, and they look like this. What do we want to do? I'm going to describe what we want to do in steps. First, we find the mean of all the data points that we have so far. Okay? Find the mean of all the data points and then subtract out the mean from each data point so that the data is centered about the mean, about the previous mean. So that the new mean is basically 0. So we take this data set, subtract out the mean so that it sort of, the data set now has 0 mean. Okay, so if we have x1 and x2 or p1 and p2, we define q1 and q2, which is just p1 minus mean of p1, p2 minus mean of p2. Okay, so that's just mean subtraction. And then we do what's called finding the first principal component. Let's call this v for a minute. We want to find the first principal component. How is this vector, this now vector, in as many dimensions as you have your data, right? In this case, if it's two-dimensional data, then v is in 2D. How is this vector defined? Let me just say what the vector is for this data set. The vector is going to be this vector, okay? It's the vector direction along which the data has the greatest variance, okay? So what direction has the greatest data variance, right? So if you look at this direction, the data doesn't have too much variance. The data is sort of very narrowly distributed along this direction, whereas in this direction, the data is very broadly distributed. So this is the direction that has the greatest data variance. That's basically the first principal component. Okay. How do we find that mathematically? Let's say we want to find some vector v, and let's say the vector v is a unit vector. Then you take each data point q and take the dot product of q with respect to v. Okay. Do q with this dot product with v for every data point in the data set. And then you try to find v such that the following quantity is maximized. This quantity is summation q dot v whole square. Basically, you're maximizing the variance. This is like variance times the number of data points. We're just maximizing that. Okay. Q dot v is this quantity, right? So if you have v and q, you project, you drop a perpendicular from q to v, and this length is now q dot v, which is called the projection of q onto v. So what we are doing, again, is maximizing the variance of the projection along V, averaged over or summed over all the data points. Okay. Once you do that, once you solve that maximization problem, we get the first principal component, which will look like this. Maybe we can denote the first principal component as W1, okay, with 1 within brackets. That's a whole vector. That's the first principal component. Next, we want to find the second principal component. To get the second principal component, take each point Q, okay, each data point Q, and then subtract out the projection of Q onto V, the first principal component. Okay, so we get this new vector R for each data point, which is Q, the original data point, minus the projection of Q onto W1 times W1. So this is a scalar, this is a vector, this is a vector. You subtract this vector from this vector. What you have done is taken away the projection of Q onto W1, right? So if you have all these data points and this is the first principal component, we take the projection onto this vector and then subtract out that projection as a vector, and what you're left is the perpendicular component, perpendicular to the first principal component. And then you ask the question, for that perpendicular component, what is the vector that maximizes the variance? Okay. So of course, in this case, the perpendicular to the first principal component is the second principal component. But if you have n dimensions, what you do is first find the first principal component, which is the vector along which the variance is maximum. And then you subtract out the contribution of that direction from all the data points. And then you have data points in the perpendicular space, which is now m minus 1 dimensional, if you're starting from an m dimensional space. And then you solve that problem again, where you ask the question, what is the vector that maximizes the variance if you project it along that vector? That's going to be the second principal component, and then you remove the projection onto the second principal component, and then do that over and over again to get third, fourth, fifth principal component, and so on. So there are m principal components, and these are the sequences of vectors that are actually perpendicular to each other, and try to explain as much of the residual variance as possible. You try to explain as much of the variance as possible, get the first principal component, subtract that contribution out, and then try to explain as much as the second principal, not explain, try to maximize the variance as much as possible along a particular vector to get the second principal component, subtract out that contribution, and then for the residual variance, try to find the vector that maximizes the variance along it to get the third principal vector, and so on. Okay, so that's how you at least conceptually define the m principal components. If you have m dimensional data, there are m principal components. This step-by-step procedure to find the principal components, which we contract as PCs, principal components, is not necessary. We don't have to compute them one by one. It turns out that we can just compute them all at once by solving an eigenvalue eigenvector problem, by doing an eigen decomposition. Okay, how do we do that? If you have this data matrix X with n data points and m dimensions, we compute the covariance of this matrix, covariance of X, which is an m by m matrix. So if you have n by m data, m dimensions and data points, the covariance of X is m by m matrix. Okay, and then you solve essentially this eigenvalue problem. You go eig of X, this S, this covariance matrix, and you get V, the eigenvectors, and D, the eigenvalues. Okay, and it turns out V contains all the principal components. V is an M by M matrix of eigenvectors. Each column is an eigenvector, and the M eigenvectors are the M principal components. So it's as simple as that. If you can do eigen decomposition, you can do principal components analysis. D is a diagonal matrix, again M by M, with M eigenvalues of S along the diagonal. The eigenvalues that are along the diagonal of D are the variances along the corresponding eigenvectors, right? So basically, the eigenvalues are the solutions, the function values for these optimization problems divided by n, I suppose, because we're finding the variance. Okay. So the variance along the first principal component will be the first eigenvalue, the variance along the second principal component will be the second eigenvalue, and so on. So one caveat is that MATLAB actually returns eigenvalues in ascending order, ascending order. In other words, smallest eigenvalue to the largest eigenvalue. In other words, the first 1, element of D will be the smallest eigenvalue, the next will be the second smallest, and so on. And the last eigenvalue will be the largest eigenvalue. So what you want to do is reverse the order, right? So a consequence of that is that when you do this command, V, the first column of V is going to be the last principal component. The last column is going to be the first principal component. So what you need to do after doing eigen decomposition in MATLAB is actually reverse the values, reverse the order of both the eigenvector matrix as well as the D matrix, so that the first column is the first principal component, the second column is the second principal component, and so on. Okay. So that's how you find very quickly the principal components of a data set. It's very fast. You can have a very large data set, and then you find the covariance matrix, which could be 1,000 by 1,000 if you have 1,000 dimensions. You just go eig, which might take a fraction of a second, and that will tell you what the various principal components are. Okay, so that's the big idea. Now let's actually check how finding the principal components helps reduce the dimensionality of the data. Okay, so we'll do that in the next video.